Well, thanks. Thanks a lot for inviting me to talk. Let me start with a warning, a dire warning. So, it's kind of the motivation for this whole thing is the motivation for what I talk about is this conjecture of Schmidt and Valonen on Hodge modules on flag varieties, but sort of what I talk about isn't really necessary for it's sort of at cross purposes. But I think it makes it makes the formulation maybe a little bit more elegant. It's just an excuse to talk about that conjecture. So okay, so you start with X, a complex manifold. Okay, and you have to be a little bit like anal about what X is, because it helps in this conjecture. So you have X is XR OX, where XR is the underlying C infinity manifold. And OX is the holomorphic functions. Okay, and then given this, you have X bar. So that's a complex conjugate complex manifold, and that's XR. Probably one way to think about it, maybe the best way to think about it, or a good way to think about it, is XR, and then OX bar is a sheaf of holomorphic functions on X bar, and those are just the anti-holomorphic functions on X. Okay, and then you have all this other bit of gadgetry that I should possibly say something about. And so APQ is just the differential on X. It's the differential forms of type PQ. Okay, and then D prime PQ. That's the currents of type PQ. And then, so most of this I don't care about, but dBXR, that's the completion, yeah. So yeah, in fact, yeah, so these guys are the only ones of these guys I care about, and that's D prime 0, 0, and that contains C infinity XR. The way if I make the indices for this right, that would be like that. Okay, now, and then the other little thing is dx is the ring of holomorphic differential operators on X. And I want to name for all of the C infinity differential operators. So I started calling it diff XR. That's the ring of all C infinity differential operators on X. Oh, it's a sheaf of rings. I mean, this is a sheaf, that's a sheaf. They're all sheaf. Okay, and then note the fundamental thing to know, the idea behind this Kashiwara conjugation business is just that you note that dx and dx bar commute in diff XR. Because just partial with respect to Z, partial with respect to Z bar is equal to partial with respect to Z bar, partial with respect to Z. Okay, maybe that's the first thing to note. And maybe the second thing to note is that, well, diff XR, it acts on C infinity functions, but then it also acts on distributions. So diff XR acts on dB of XR. So that means that dx and dx bar, they both act on distributions, and they commute the way they act. Okay. Okay, and then we have all these categories. So we have dx mod. That's a category of D modules. D modules. And then among these, we have some good ones. We have RH dx, that's the regular holonomic demodulus. And we have, so with the category of perverse sheaves, it doesn't really play a role in what I'm saying, but maybe motivationally it does. So perv XR, that's a category of perverse sheaves. And yeah. And then you have this theorem, the famous theorem, Kashiwara and Mepkut, I guess. That we have an equivalence dr, and that goes from the regular holonomic dx modules to perverse sheaves on XR, which is kind of, well, I mean, one thing to think, well, one thing kind of maybe motivates this next thing I'll say is that this would be, the perv XR doesn't care if you use dx or dx bar. It doesn't really care about that. It's the same thing, right? Okay, so oh yeah, there is an equivalence. There exists. Yeah, there exists an equivalence. For yeah, I always put in degree minus n. I follow you guys. I mean that's what I do because it's how I learned it. Okay, yeah. Now, oh yeah, I skipped a page. Yeah. Okay, so now definition. So how I think maybe how Kashiwara conjugation started is that he wanted a real. I don't know what he really wanted, but he wanted. Maybe it seems like he probably wanted a really concrete way to understand the way Verdier duality works over on this side. Maybe let's say that's what he wanted. So suppose M is a dx module. Okay, the Kashiwara conjugate of M is this pretty simple thing. I mean, it's really kind of cool. You take the Hom, so K of M, I'll call it K of M. It's the Homs over dx from M into the distributions over XR. Okay, and then the observation is that since dx and dx bar, they commute inside the ring of differential operators, this guy, he still has an action of dx bar on it. So this sucker right here is a dx bar module. So this is a dx bar module via the action on the dx bar action on dB of XR. Okay, so and then he proved this theorem. So this Kashiwara, and it's from kind of a longish time. I mean, pretty long time ago, maybe. So sometime in in the 80s, when people were doing all this in the 80s, sometime in the 80s, 87, I think. So the Kashiwara, the functor K, induces an equivalence K from RH of dx, so op to RH of dx bar. Okay, so so maybe I want to make some remarks about this. Remarks. Okay, one, the equivalence is C linear. That's maybe so. That's the obvious So C linear equivalence. That's obvious, I guess. Okay, the other the proof is pretty simple. I mean, what he does is kind of clever. I mean, he has to use some like analytic thing, and that analytic thing is this theorem of I guess Atiyah and Bernstein and some other people about division of distributions. It basically causes these D modules to have solutions, distributional solutions. But then he reduces it to really the one-dimensional case. He kind of gets by blowing up and doing kind of putting himself in the normal crossing case and all kinds of other, you know, what do they call it? Devisage. He like reduces it to the one-dimensional case, and then he just has to use. Then he uses the big, you know, kind of big theorem. So maybe the proof is simple. But uses Atiyah Bernstein. I think it's Atiyah Bernstein, result on division of distributions. I mean, it's simple in that it's like kind of short. The paper is pretty short. It's like four or five pages. Okay, so now there is another. Let me make another remark, which is that there's another operation that takes you from dx modules to dx bar modules, which is actually also an equivalence, but which is even simpler to say what it is. So there's another operation. Let's call it just conjugation. Conjugation, C from dx mod to dx bar mod, induced by just taking the a differential operator and barring it. Induced by the homomorphism. So dx goes to dx bar. Just p, you send it to p bar. Okay, and so that's also an equivalence, but it's not linear, it's conjugate linear. So this induces an equivalence. So RH, well, you wouldn't need the RH here really, but if you respects that, RH by C to RH dx bar, and it's not, as I said, which is conjugate linear. Okay, so that I don't know what to do with it. I kind of realize that people can't always see this board because everything's sitting there. Okay, there. Okay, and then maybe. Let me write it's kind of fun for me to write down the example because I like it. Because this is actually, I learned about this kind of stuff here like 10 years ago. So, it's kind of nostalgic for me to write down this example. So we have x equals a1, and j is u. J is the map from u equals a1 minus 0 to a1. And let's set let I is the map from 0 to a1. Okay, so we have an exact sequence. So we have an exact sequence of dx modules. And then I'll write down the perverse sheaves because sometimes it's easier to think about perverse sheaves. So 0 goes to OX, goes to I wanted to write this. Let's call this guy D. OX star D. I mean, I'll say what this means. It just looked really weird to write star 0. And then that goes to let's call the co-kernel S. Okay, so here OX star D, maybe I have to write on this side. OX star D, that means the functions, the functions that are meromorphic. They're holomorphic on A1 and meromorphic at D. No, I'm going to put the perverse sheaves, right? So, yeah, I wanted to explain what these people were, but no, I'll just kind of do this. So this, how does it look in dx? So it goes to C shifted by 1 on x. And then here we have J lower star of C shifted by 1. And then here we have I lower star of C on 0. That's what this exact sequence goes to. And here OX star D, that's meromorphic functions that are with holomorphic functions on A1. Which are meromorphic at D. And this S, one way to think of this S is this dx of the delta function. That's one way to think of S. Okay, so and also OX star D is generated by OX star D. You can also think of it as dx of 1 over z. Okay, now, so what I want to just see what Kashiwara conjugation does to this because this is kind of cool. So it's semi-cool. So another way to think of dx times 1 over z is also dx times z bar over z. And this is kind of maybe the better way to think about it because that way this is a kind of it's an L1. It's an L1 function, so it's kind of a priori a distribution, gives you a distribution a priori. So so now I want to. So let's set. Maybe I make this claim. It'll just look. Let's set n equal to k of OX star D. And my claim is that that guy is dx bar of just z bar over z. Yeah, it doesn't. That's why they're the same thing, yeah. No, I mean, it acts. It just acts in a way that doesn't act. It's just partial with respect to z of z bar, right? So anything in the whole distributions, right? The whole ring of distributions, it acts, right? So the whole ring of distribution, no, not ring. The distribution is not a ring. The whole sheaf of distributions is one big, giant, totally not coherent or quasi-coherent dx module, right? Because dx acts on it. Because dx acts on it, dx bar acts on it, they both act on it, right? So, yeah?
So when you write that, you mean the dx submodule of ddx are?
This means, this doesn't really mean much the way it's written, although it's kind of, you can make sense of it, but this guy is contained. When I write this, that means it's contained in this guy right here, which is itself a dx module, right? This guy, the distributions, because dx is acting on that one.
So what is the value of dz of 0?
Yeah, it doesn't. But then the cool thing, I'll show you the cool thing that happens. I mean, there's a kind of neat thing. I'm about to show you the neat thing. So what is this guy? So now so then you get, so if you do this, then you get an exact sequence. So the Kashiwara conjugate of S is just S. Maybe that part is going to be boring. So n to OX bar. And and this S, that's a delta function, and all I want to really explain is why you get the delta function. That's the cool part. That's the part I think is cool. So what it is d bar, so d by dz bar, I'll just write it d bar. D bar of z bar over z, that's equal to 1 over z, right? what do I want to say this? But d bar of 1 over z, that's not equal to 0. That's the delta function. So that's how you see the delta function sort of living in this guy right here. And if you dr this, oh maybe this is taking too long. Yeah. If you take dr, so I'll write this down again. This goes by dr of x bar to 0 goes to I lower star of c, goes to j lower shriek of c shifted by 1, goes to c shifted by 1. To 0. Yeah. I don't know if I explained that really well. The cool thing is that d bar of z bar, d bar, yeah? Yeah, I might. Yeah, there probably is that part, yeah. Oh. Oh, yeah. Oh, okay, yeah. Well, yeah, I mean, I'm sure, but is it, I mean, I should know this, but is it 2 pi I upstairs or downstairs? Pi I, 1 over, okay, yeah. I mean, oh, it's upstairs. Yeah. Okay. Oh, yeah, that way. Oh, yeah. Oh, sure. Yeah. Okay, that way I totally understand. Yeah. Yeah, that is the Koshiina. That's what they. Yeah. I mean, I've seen it before. I actually saw it written on the wall in a bathroom in Trenton, like at a punk. Sort of punk rock club that they used to have there. Trenton. Okay, so now, yeah, I better. Yeah, well, I know that's kind of going to be an important. Well, that's not really that important, but okay. So suppose A is a ring of twisted differential operators. So I'm supposed to kind of tell you what this is, and I kind of want to not kind of do that in a in a way that I'm capable of. So roughly, this is a sheaf of rings on X, which is locally isomorphic to dx. So and in a way that respects the order of differential operators. Okay, so maybe the better thing I mean, you can look up the definition in a book, But so dx comes with a filtration by order of operators. And then fp should also come with that. You notice that f1 of dx, that's just ox plus tx, where this is a holomorphic tangent vectors, and this is like just a ox. And for A should also have a filtration. Also should come with the filtration. I mean, the part of the definition of A is that filtration, but I didn't want to write down the definition of A because I felt like I might get it wrong. And it's but then F1 of A is you don't require it to split, but rather you have an exact sequence. 0 goes to OX, which is F0 of A. That goes to F1 of A, and that goes to TX. That's what you got. This is not necessarily split. Okay, and then from this, you get an element of X1 TX OX, so that's you get an element of H1 of omega X. And that would be that. That would be that's a, and that yeah, that's kind of the primordial example. And actually, if it were differential operators on a line bundle, then what I talk about is kind of, well, it's already known, really. I mean, to some extent. So, so that's equal to H1 omega X. Okay, but that's not, so this class, it kind of, for some things, it kind of determines what the twisted differential operators are completely, but, you know, there's a fact. Let me just say the fact, and then maybe I'll I'll give an explanation, a little bit of an explanation. So let's set TW of dx equal to isomorphism classes. So they call these rings of twisted differential operators TDOs. So let me just call it that, TDOs, rings of twisted differential operators. Then this thing is equal to H1 of DOX. And it's not so hard to prove because what you have is sort of locally, you have an isomorphism, the isomorphism of dx with A. And kind of everything is really determined by what goes on in the F1 of A. Yeah.
Are the graded pieces globally isomorphic to graded pieces of A globally isomorphic to the graded pieces of TX?
They wind up being, yeah. Because the graded pieces are globally isomorphic to sim and TX, yeah. Because they wind up being like that, yeah. That's probably part of it. That's either part of the definition or it's a consequence. But yeah, so yeah, what I want to say is, I mean, I think it's essentially this. It's locally, they'll cover X by some U alpha. Okay, then you have some phi alpha from dx restricted to U alpha. So the isomorphism to A restricted to U alpha. And then phi alpha inverse of phi beta of partial with respect to Zi. By that exact sequence, it has to be partial with respect to Zi plus some Fi. And then what you see is, but then these guys have to commute, right? Because partial with respect to Zi and partial with respect to Zj commute. So you get a one form. You get a closed one form. So since partial with respect to Zi, partial with respect to Zj is equal to 0, maybe I'll just make kind of a long story short. The omega equals sum of Fi dZi is a closed one form. So you get that one. Because these, you know, Poincare lemma kind of thing. Okay, so yeah, so maybe there's a let me point out this corollary of the fact, which is that so you have H1. You know, it's kind of easy to figure out what the twists all are. So you have H1 of XC goes to H1 of XOX goes to the set of isomorphism classes of twists, and that goes to H2 of C. H2 of XC, and that goes to H2 of XOX. So just by applying the exact sequence, so if X is compact Kähler, which kind of is a good case to care about, So if X is compact Kähler, then the the isomorphism class of twisted differential operators is just H20 plus H11. Because you see that, I mean, if it's, yeah, you all probably all see that. Okay, so, and then if X equals G mod B, which is actually, so a generalized flag variety, then T of dx, and that's just, well, it's pick of X tensored with C. Yeah, you just land in that, but you should think about it really seriously. Because that C1, he's like a complex element, you know, with the, put in all the twists and all that kind of thing. Really, but yeah, that was a joke, really. Yeah. Okay, so now what my goal, the goal is I want to take one of these rings of twisted differential operators and I want to embed it in the ring of all differential operators. That way I have like a concrete way of seeing what that is. That's actually what I like about this whole thing. So I want to make this business as explicit as possible by kind of replacing this sort of derivation by kind of something about the Dolbeault complex. Okay, so so D of OX, that's quasi-isomorphic to omega x bigger than or equal to 1. So all I'll do is I'll resolve omega x bigger than 1 by the Dolbeault complex. Did I do something? Oh, shifted. Yeah, maybe. No, yeah, well, it depends on where you put it. If you start omega x shifted, yeah, maybe, so shifted by 1. That's probably true. So I'm going to resolve this guy, and then I'll just explicitly say what the elements of H1 of DOX are. So let's do that. So we have omega x1 goes to omega x2, etc. Goes to A1, 0 goes to A2, 0. No, these are the wrong way. No, they're going the wrong way. A1, 0 goes to A1, 1. Goes to A2, 0. Goes to A2, 1. Blah, blah. Okay, and I think that's all I need. And while these are B and these are D bar, D. Okay, and then what we see is let's set ZD of x equal to the things that would give us the things in this resolution that would give us one closed forms. So that would be the pairs lambda omega in A1, 1 plus A1, 0, A2, 0, such that D bar lambda is equal to D omega is equal to 0, and partial lambda is equal to D bar omega. And then let's set B of dx equal to the set of D bar of gamma, partial gamma, such that gamma is in A1, 0. Okay, and then, then this twist of dx, that's just z dx mod b dx. Okay, but yeah, sorry about that. Right, yeah. Okay, so now here's what I do. Okay, let's set d lambda. So let's suppose lambda in A11 is both d and d bar closed. Okay, so let's set. So then it gives a class in here because you could put lambda lambda 0. So let's put d x lambda equal the twisted d module corresponding to lambda 0. Okay. So then I want to tell you what that is. That's the whole goal, really. So, okay. So the way I want to tell you what that is, I want to tell you what F1 of it is. Because that kind of, like I said, F1 kind of determines the whole thing. Okay, so here's what F1 is. So set E lambda equal to the set of pairs F V in C infinity x plus Tx such that for all anti-holomorphic vector fields W, W of F is equal to lambda VW. So it's kind of cool. It's like a kind of Cauchy-Riemann equation, but they're kind of twisted a little bit. Okay, so so you can view E lambda as contained in the differential operators on XR just by sending FV to F plus V. Okay, and now I want to say theorem. So suppose lambda is as above. So d lambda is equal to 0. Then you have 0 goes to OX, goes to E lambda, goes to TX, goes to 0. Okay, so where this map is just you send F to F comma 0. And this map is you send F comma V to just V. And that's an exact sequence. So it's exact, the sequence is exact. And it generates that E lambda inside of this diff XR, it generates a D modulus isomorphic to DX lambda. So what it does, it has the effect, it puts dx lambda inside the ring of differential operators. So in particular, so it makes it act on distributions. And maybe I have one little, well, let's make a comment. Oh, yeah. Well, let me make an observation, which might be helpful. So there's another way of seeing this. Okay, so suppose lambda, and which maybe is more better and more elementary. Suppose lambda is equal to d bar log of phi. Okay, so locally they are all going to be like that. But then dx lambda, what that is just L phi inverse of dx times L phi, where L phi is just multiplication on the left by phi. And that's cool because if you want to get if you have a dx module, you can make a d module by just kind of multiplying that guy, that dx module on the left by L phi inverse. So so if M is a dx module, L phi inverse of M is a dx lambda module. It's because the conjugate, the way the conjugation works. Okay, now so now I can read. I need to make one observation, and then I can say the kind of main theorem, and then I can talk about the real stuff. Okay, so the observation is that dx lambda, he commutes with dx bar minus lambda in this diff xr. Okay, so if M is a dx lambda module, then so if M is a dx module, K of M, which you do the same way before, it's Hom dx lambda M into distributions is a dx bar minus lambda module. And then the theorem becomes I'm going to state the theorem, but the theorem it's pretty easy because Kashiwara's proof is kind of local, so proving the theorem. No, I want to. Maybe I'll erase this. So the theorem becomes that you get an equivalence of categories, just like before. And maybe I should say, so in the case where X is G mod B, so Kashiwara and Barlet, they proved kind of equivalent. It was a pretty equivalent state. I mean, I like the way this is set up better, but okay. Yeah. So maybe like one little remark. So as in the untwisted case, you have a map dx lambda goes to dx bar lambda bar by p goes to just p bar. And then let me make a definition. Let's call a module polarized if m bar if there's an isomorphism between m bar and k of m. M is an isomorphism. And then maybe a remark, this can only happen if lambda is equal to minus lambda bar. Lambda bar can only happen for lambda minus lambda equals lambda bar. Because they have to be, it wouldn't make sense otherwise. So in other words, lambda has to be pure imaginary. So all the guys that come from the D of line bundles, those are pure imaginary because they're sitting in like 2 pi I times C. The I becomes important. So those guys, in fact, those line bundles themselves are D modules for D of that line bundle, kind of by definition. And those guys are polarized for some obvious reason. Well, they are. I'll just don't ask me why, but they are. Okay, so now, polarizable. I don't know, polarizable. Okay, so now I want to talk about just one more thing. So a polarization gives a pairing. M tensor M bar to dB of XR. And it's like bilinear. It's dx bar acts on dx acts on this, dx bar acts on this, and they both all commutes. And this is the way like Sabah sets up the whole. This is what he called the polarization. This kind of thing exists. Sabah uses this. Okay, so now. Okay, good. This is good. Okay, so now I talk about Schmidt and Vallone, they make these beautiful conjectures, which are a little bit hard to explain, but I want to explain them kind of by examples. So suppose X, here's their idea. Suppose X is a complex manifold and with a volume form. And then suppose M is polarized. I guess polarized dx lambda for some lambda. Well, you can do this thing. So you wind up with M tensor M bar goes to distributions on X. Okay, and let's call that angle bracket. But what you can do this smart thing, because you have the volume form, you can just take global sections and you can just integrate them over that volume form. So you get so you get a pairing, and it's kind of, well, since you have M and M bar, you can think of it as a Hermitian form on the global sections of M. It is a Hermitian form. It actually is a Hermitian form on the global sections of M. Okay, so but their conjecture has to do with this pairing, but in a particular case. So in Schmidt-Vallone, you have X is GC mod B, where okay, G is a real reductive group. B contained in GC is Borel. The volume form is the standard one. So standard one means it's invariant under the compact form of G. Okay, and then it might come up that K would be a good name for the maximal compact of G. So K is going to be the maximal compact of G, but that doesn't come up quite yet. Okay, so and then it might also come up that rho would be a good name for the half sum of the positive roots. So rho is the half sum of positive roots. That might also come up. Okay, so the conjecture, it has to do with Hodge modules on X. So I'm not going to say what those are because I definitely messed that up. But they're D modules, and they come equipped with some filtration, which we call the Hodge filtration. There's increasing filtration. We call that the Hodge filtration. Okay, so conjecture has to do, so strictly with K equivariant, K invariant Hodge modules. On X. Okay, so these are D modules, well, or in general dx lambda modules, M, equipped with Hodge filtration, FP of M. Yeah, I mean, we're just there. Yeah, I think so. But some things about this are not, maybe they could be written down probably better by somebody. But certainly there are tricks that you can use to make it use regular technology. But well, let me just say the conjecture. I want to work in an example where it's pretty clear. I want to give an example of the conjecture where everything is kind of clear. But let me just state what their conjecture is first. Okay, so you have to assume that lambda is bigger than or equal. In my notation, lambda is bigger than or equal to minus rho, but for people that think about these things, I should have shifted by rho in the first place. So m is k equivariant dx lambda module. Okay, and then you start off. Let's make which is the Hodge module. Okay, and then we make a normalization. So let's make it so f minus 1 of m is equal to 0, and f0 of m is not equal to 0. Okay, then the conjecture is that this form has sign minus 1 to the p on h naught of fp of m intersect h naught of fp minus 1 of m perp. That's the conjecture. Well, see, the Hodge filtration, it's not really kind of honest to call it the Hodge filtration because all these modules, they have completely stupid Hodge filtrations on the open part. In fact, they're just made of either constant sheaves or like sheaves with very little monogomy on the open part. But then on the boundary, it kind of grows, and so yeah, that's all I want to say. I mean, it's not really. See, this is not really, in a way, it's not really about Hodge theory. No. Maybe I might be assuming that lambda is not an integer. Very soon I will be. But now lambda can be an integer. I mean, these things become very. The nastiness happens at the integers. But okay, let me make an example. So we can do an example. What? Oh, for the. Oh, yeah. Well, okay, yeah. Okay, there's a little lie that I probably said. Maybe I put a bar here too, but there's probably a lie I said, which is that. So the Hodge module, he comes with a polarization, right? Okay, and the lie is the bit that's probably not completely nicely written down. I mean, the Hodge module comes with a polarization in the open part, for sure, and the way Saito works it out, it induces a polarization on the whole thing. But the problem is that what Saito defines to be a polarization is not the same as the way this is the polarization. And they should agree. They pretty much have to agree. Everybody agrees to agree. But yeah, somebody should write that down. That's probably what I should be talking about. I mean, yeah. But you can kind of see it because on the open part, you get functions that the polarization winds up being sort of integrable. So you wind up, even as you go to infinity, you have like locally integrable functions at infinity. And then taking derivatives of that, so you get distributions. Okay. But let me do, so if you look at an example, it's kind of fun to look at an example. So they've proved in a lot of cases. Min and Valonen proved in a lot of cases. But in the case of SL2, you can just check it all explicitly. So all kind of explicit, and it's kind of fun. And it also has to do with like cool integrals that I actually learned about in physics situation. Just kind of, I don't know. Okay, so the stupidest example, x equals p1, m is equal to dx times the delta function. You know, we view that as contained in dB of xr. Okay, and then the volume form, so there's i's that I'll probably mess up. And everything is about signs, but there's probably 2 pi, I don't know what it is. One. But the volume form is like that, dz wedge dz. The important part is dz wedge dz bar of 1 plus z squared, right? Now, so now what is the Hodge filtration on this character, this m here? So fp of m is delta naught, partial of delta naught, all the way up to partial of, see if we did it 0, we just have delta naught. So partial p of delta naught. All right? So, and those are global sections. Obviously, everything's supported at a point. So partial P delta naught, partial Q bar delta naught, that's equal to partial P partial Q bar delta naught evaluated on this 1 over I dz wedge dz bar over 1 plus z squared squared. Okay, but now what is this guy right here? Now here comes the cool part, which I think is just crazy, but this the way it is. So this, we can move the guys, the delta, well, let me write it like this. So this is equal to partial P partial Q bar 1 over I. Okay, and I'm going to write it in a different way. I'm just going to expand this guy out. So this is the sum from minus 1 to the P, of minus 1 to the P plus 1, absolute value of Z to the 2P. So I've kind of dropped the DZs and GZ bars. Let's not, once we're in this affine part, they don't play a role. Okay, and then, well, I take the P and Q bar into that, but what I'm going to get, I'm going to wind up hitting this, oh, where did I lost the delta function. So what I get, so what I do is I have the delta function, I have to move these guys over, but then I take derivatives over here. So what I get is that this is equal to 0 for P not equal to Q, and it's equal to minus 1 to the P times P plus 1 times P factorial squared for P equal to Q. I hope that's visible. And it's just because what do I have to do? I have to take P derivative, well, this Z to the 2P is, this absolute value of Z to the 2P is Z to the P times Z bar to the P. And I have to take P derivatives of it both times. I'll get P factorial, and I'll get the P plus 1. But the important point is the minus 1 to the P. Okay, so so the remark, oh yeah, very little time. The remark is that, a cool remark to make is that this conjecture, it really depends on what that volume form is, right? If instead of having dz wedge dz bar over 1 plus d squared squared, I just had 1 down there, then all this would all be nonsense. Or if I had 1 minus z squared, it would also be nonsense. So it's very highly dependent. Okay, so remark. Okay, and I have one more. Heavily dependent on the volume form. Okay, then there's one more thing, and then I kind of go. So I'm going to cut. So yeah. Okay, there's one more. There's a couple. Well, there's a few other types of D modules to which the conjecture would apply, and one type. Let me just. I'll kind of tell you the answer because I don't have enough time. So one time is like, let's take C, I guess bigger than minus 2, C in R. Okay, so we can have MC, oh, this is going to be hard to write. How much time do I technically speaking have? Okay. Oh, okay. Well, let me just write something down, and do, I don't know if it's going to be comprehensible, but I'm gonna try. I'll do my best. So there's a twisted D module that I can put on P1, which looks like this. It looks like dx lambda times z to the c over 1 plus z squared squared, or d to the c. Okay, and you can figure out what the Hodge filtration is. So the H naught of Fp of m. That's gonna, well, it's gonna consist of guys that look like z to the c times z to the k over 1 plus z squared to the c, where k is an integer. Oh, and maybe I assume that c is not an integer. Okay. Okay, well, k is an integer, and the way it works out, absolute value of k is less than c over 2 plus p plus 1. Okay, I actually, that's what it works out. That's what H naught of P actually is, I promise. Kind of, you can trust me, I think. Okay, and then how do you prove the conjecture? Well, you can actually do these integrals. So you set fk equal to this thing, z to the c, z to the k over 1 plus z squared to the c. What you get is that fk times fk bar, that winds up being this integral of absolute value of z to the c plus 2k over 1 plus z squared to the c times the volume form. And you can actually do this. You stick it into polar coordinates and do it. Just do it. And then winds up being gamma of c over 2 plus 1 plus k times gamma of c over 2 plus 1 minus k. And that's cool because what it means is that, so this f naught, you see that f0 can be kind of big because when p equals 0, if c is big, you still got a lot of stuff in there. So, and if you look at this guy will be positive if both of these terms are positive. But then after that, the signs start to alternate. One of these guys, once this argument of the gamma function becomes negative, the signs alternate through the intervals. That's actually how it works. That's all. I'm out of time, so I'm not going to say anything more. But that's how it works.